and welcome to this next lecture in this course on pattern recognition. We have been essentially discussing the support vector method and the kernel function based classifiers. So, we will continue with the discussion this class also. We have looked at the support vector method both for classification and regression. We have seen the support vector machines for classification and also looked at the support vector regression. Okay. In both cases, there are certain things that are interesting. One is that the optimal parameter vector is given by the linear combination of a subset of the training data. Okay. The linear combinations coefficients happen to be the Lagrange multipliers or some function of the Lagrange multipliers in the of the automation problem, but essentially the W is given as a linear combination of the training vectors, the support vectors. And we have seen that the kernel trick allows us to learn nonlinear models using essentially linear techniques. This is because the kernel we can kernelize the inner product. So, any algorithm that essentially has only inner products can be implicitly be executed in a high dimensional space using the kernel function. So, these are essentially the two basic characteristics of the support vector method that we have seen so far. Okay. Now, what we have not fully discussed, even though we mentioned it just briefly towards the end of last class, is how does one actually solve the learning problem of support vector machines. Learning of the support vector machine involves a constraint optimization problem, and last class we seen how to an example of solving this constraint optimization problem for a very simple example. It's in R2 learning a quadratic classifier with only 3 examples. Though it is a simple instance, it does tell us the more involved the issues involved in solving the automation problem, but we need more generic methods. We briefly mentioned, we just recall them once again. So, in this class we will briefly look at the general method that people propose for the solution. We are not looking at any method in any great detail, because most of these algorithms simply happen to be specialized in numerical optimization techniques. So, algorithmically once you formulate the optimization problem, there is not much more, there is nothing much more conceptually to convey, except that these are very interesting specialized numerical techniques for solving the class of automation problems that are of interest in SVM. Okay. So, this is the automation problem, as you already seen. This is the automation problem that we need to solve. It is a quadratic automation, quadratic programming problem. We have a quadratic cost function as a linear term summation mu I and a quadratic term mu I mu j y I y j k x I x j. Essentially, this is the quadratic form with respect to the mu vector of the matrix whose ijth element is y I y j k x I x j. And I have 2 constraints. One is a linear constraint, linear equality constraint, mu I y is equal to 0. Another, the rest of the constraints are simply bound constraints on the variables. So, it is a standard quadratic programming problem with a quadratic cost function and linear constraints. So, what we need is a nice numerical method. Of course, there are many numerical methods for general nonlinear programming problems. For example, I can use constraint gradient descent, gradient projection, or one can use penalty method, barrier method. There are many such standard numerical algorithms for solving constraint operation problems. But we can do we can certainly do such gradient descent based methods, but this problem has a lot of extra structure, right, and because of that many more efficient algorithms are proposed, right. This essentially only bound constraints on the variables, which are very simple to implement. There is only one equality constraint, and this is a very nice quadratic form. So, there are a lot of interesting things you can do with it. Okay. To actually look at the structure, let us look at the conditions for optimality of this problem. We are asking, given some mu1, mu2, mun, when how can I say whether or not they are optimal. So, it simply means whether or not they satisfy the Kuhn-Tucker conditions. So, by writing Kuhn-Tucker conditions and doing some algebra, we can show that these are the optimality constraints. If you give me mu1 mu_n, then I will define f(x) as mu_i yi k xi x plus b, where b is given by this for some mu_j greater than 0. As you can see, these are the standard solutions we could have got for w on b if mu were the optimal thing. Then with respect to such an f, this is what all I have to satisfy. For every I, if mu_i is equal to 0, then yi of xi should be greater than or equal to 1. If mu_i is strictly between 0 and c, yi of xi is equal to 1, and mu_i equal to c, then yi of xi has to be less or equal to 1. Right. So, this is the optimality constraint. So, essentially it is as if every mu_i is tied with one example, right. Even in our constraints the primal, every mu_i is tied with because of every constraint in the primal is tied with one example, every mu_i is tied with one example. So, I can say which examples mu_i this is, and each mu_i is essentially has its own condition, because it is not completely decoupled, because f(x) depends on all the other mu's, but really I can ask which mu's satisfy the constraint, which mu's do not. Given the current f(x), if I think of f(x) as given and do not worry about it being a function of mu, I can individually ask which mu's satisfy and which mu's do not satisfy the optimality constraints. So, given this kind of a structure, there are many interesting tricks you can do in optimization, and one standard such trick is what is called a chunking. Chunking is a very generic idea in optimization, where even though you have a optimization problem with large variables, we will optimize only on a few variables at a time. The standard chunking that most of us know about is the coordinate wise optimization. If I have an unconstrained optimization Rn, a simple thing to do is to first optimize with respect to first variable x1, then with respect to x2, then with respect to x3 and so on. The idea is that all one dimensional optimizations are simple, right. So, in general chunking, the idea of chunking consists of optimizing on only a few variables at a time. Its utility is that the dimensionality of the optimization problem is controlled. Of course, we may not want to do one at a time as in the coordinate wise optimization. So, maybe I have a optimization problem or 1000 variables, I may be doing 25 at a time, right, or 50 at a time or 20 at a time. The idea is, because the quadratic programming problem, if I take only 20 variables, I have a quadratic form with 20 by 20 matrix, which is much easier to solve than a cost function which involves quadratic form of 1000 by 1000 matrix, right. Basically, the idea of chunking is that at our iteration I choose, let us say, a 20 or 25 variables to optimize on, okay, and only for that many variables I run the optimization algorithm, and I keep randomly or through some heuristics keep choosing subsets of variable to optimize, and normally this speeds up the entire optimization, okay. And this idea gave rise to the first specialized algorithm for SVM, which is called SVM Lite. Even today, possibly one of the most popular SVM algorithms, easily downloadable. If just from any web browser, SVM Lite will tell you how to download SVM Lite. Freely available software and very good for experimenting with, okay. So, SVM Lite essentially uses a chunking idea to solve the SVM optimization problem. Now, as we seen, chunking is basically do a few variables at a time. So, I can ask what is the extreme chunking I can do, what is the smallest set of variables I can optimize on. Can I do coordinate wise optimization in this problem? I can't, because the mu_i's have to satisfy one equality constraint, mu_i yi, summation mu_i yi is equal to 0. What it means is, if I am currently at a feasible point, so I am at some mu1 mu2 mu_n which is feasible, meaning which satisfies all the constraints. If I change only one mu, keeping everybody else same, obviously I will go out of the feasibility region, because I can no longer satisfy the equality constraint. So, because I have an equality constraint, if at every iteration I want to move from a feasibility point to a better feasibility point and so on, I cannot get rid of feasibility. So, I have to at least consider 2 variables at a time. So, the smallest chunk that I can optimize on is 2. So, there is an algorithm called sequential minimal optimization. It is called minimal because it works only on 2 variables at a time. The earlier we said that by doing chunking, by reducing the number of variables to optimize, we are improving the I mean improving the numerically or speeding up the algorithm. So, choosing only 2 at a time is very nice because we do not even need a numerical optimization technique to actually optimize with respect to 2 variables. So, this is the algorithm SMO. So, SMO method optimizes 2 variables at a time. It always maintains feasibility, that is at any given point is at a feasible, at any given time in the algorithm is at a feasible point, and then it chooses some 2 variables to optimize and comes to a new set of values for those 2 variables in such a way that I am still in the feasible region. Okay. It always maintains feasibility. Basically, what it does is keeping all other mu I fixed. If we changes only 2 of them, let us say mu 1, mu 2 are being changed. So, mu 3 to mu n are all kept fixed. Then my quadratic form of the objective function, if I can always take away all the terms involving only mu 3 to mu n, then I just get some quadratic expression in mu 1 and mu 2. Now, that is very easy to optimize. I can analytically find the optimum with respect to those 2. So, keeping all the other mu I fixed, if you want to change only 2 of them, we can calculate the updates for them analytically very easily, which means I do not have to spend my time doing numerical optimization. So, I can spend most of my time in deciding which 2 variables to choose at each iteration. Now, I have separate optimality conditions to be satisfied by them. So, I know which all variables are not satisfying optimality right now. Out of them I can choose 2 based on some heuristics. So, there are large set of heuristics in SMO which are employed to decide which 2 variables to choose, and the resulting algorithm is extremely efficient. It can solve tens of thousands of variable SVM problem very fast even on a simple computer. Okay. So, SMO is for a long time one of the fastest algorithms for solving SVM. Today there are many other recent additions to this, but possibly even today SMO is one of the simplest in the sense of conceptually simple, pedagogically also simple to explain, one of the simplest algorithms that is still very efficient to solve SVM. Most of the freely available packages use either SMO or SVM Lite for solving the SVM optimization problem. Because there are many other techniques. For example, here is another technique proposed, which is also quite efficient compared to SMO. It is just a little bit involved to actually give the details. The basic idea is the following. Suppose you have a 2 class problem with linearly separable patterns. When we did the VC dimension proof for hyperplanes, we actually saw that 2 sets of points are linearly separable if and only if their convex hulls are separable, right. So, basically if I have 2 sets of points which are linearly separable, I mean we have 2 class problem with which is linearly separable, then if I take convex hull of class 1 and convex hull of class 2, then those will be separable too. Then I can ask what are the 2 closest points on the 2 convex hulls. That is, I want to pick a pair of points, one on each convex hull, which are closest to each other. Now, they are called nearest point methods, and there are some very efficient algorithms in computational geometry for such things. And one can show that the optimal hyperplane, as we defined earlier, will be the line that perpendicularly bisects the line that is joining the 2 closest points. Right. Now, this idea can be used, of course, you still need to, this is only in the linear case, I have to make this thing work with kernel function, but this idea has been used to develop a very interesting and highly efficient algorithm for SVM optimization. So, like this there are many other techniques. Okay. So, we stop there, and so we considered the entire SVM support vector method for both classification and regression. We will see some generalizations of the kernel idea, but before that let us ask the question, okay, now that we have considered one more method for learning nonlinear classifiers, how good is this? As it turns out, it is a very competitive method for tackling most PR problems. Today, the state of art is such that if you are trying out a off the shelf algorithm on your problem at the first cut, unless you have very good reason, you have to first try SVM. For example, if you are a researcher and you are writing a paper and suggesting a new method, the one thing against which you have to benchmark your method is a SVM. So, SVM has become that kind of a standard in pattern recognition today. Okay. Now, SVM meaning SVM and all the kernel based methods. It's possibly more today is much more of a complicated method than neural network methods we consider earlier, but that is not to say that neural network methods will not work, or for every problem SVM is good. Obviously, it does not generate magic classifiers, but all the same, learning a nonlinear classifier only involves choosing a kernel function here, and choosing a kernel function is much easier because I am just asking the kind of separation I want, as opposed to choosing whether I want one hidden layer or two hidden layers, how many hidden nodes I want in a neural network case. And also for let us say if you are using feed forward sigmoidal networks, I have the problem of local minima. Here the SVM optimization problem does not have the problem of local minima. So, learning nonlinear classifiers with SVM is certainly very attractive, because all it involves is choosing a kernel. Of course, it is not as simple as that. User still needs to make choice of parameters. I have to choose kernel function, but I also have to choose parameters in the kernel function. For example, if I am using Gaussian kernel, I have to choose what the sigma in the Gaussian kernel should be. Second thing I have to choose is the C parameter, the penalty parameter in the optimization problem. I have to also choose parameters in the optimization problem. For example, in any numerical optimization, I have to choose an epsilon which is equal to 0. So, when I am trying to say for checking optimality, if I have to say y I f x I is equal to 1, obviously I have to ask to what precision it should be 1 in numerical technique. So, I have to also choose an epsilon. So, all these choices are still there. Bad choices can still result in overfitting, but given that still SVM is possibly one of the most competitive methods for tackling PI problems today. The second very interesting thing about SVMs are the support vectors. As you see in the support vectors are the training data which are closest to the class boundary as well and closest to the optimal subtraining hyperplane. Of course, this hyperplane is in a high dimension space, they are essentially closest to the class boundary in the original space. So, these themselves are a very important extra information that the support vector method gives me, because if I know that these are the patterns that are closest to the boundary, in some sense I know these are the hardest samples to learn to classify. As a matter of fact, in the SVM method as we saw, once we get our optimal hyperplane, if now I keep only the support vectors and throw away the rest of the examples and once again solve the operation problem, new operation problem only on this, I will learn this exactly the same optimal hyperplane, right? Because the support vectors are the most important thing. Once I classify the support vectors right, the rest of the things will be automatically classified right. So, in that sense, support vectors at the end of the thing, I am not only just getting a classifier, I am also getting the support vectors, which is a very useful extra information that the method gives me. Matter of fact, in the sense that they define the class boundary, maybe now a nearest neighbor classifier which just uses support vectors as prototypes will do very well. As a matter of fact, in many applications such things are tried. So, I will just show you two interesting cases of which illustrate both how nicely the SVM method classifies as well as the utility of the support vectors. Okay. Here is the first example, is a 2-class problem. One class is shown with slightly darker things than the other. Actually, we have crosses and squares. I suppose all of you can see that is a 2 by 2 checkerboard problem. And we have at the center 2 lines. So, this quadrant and this quadrant is one class, this quadrant and this quadrant is other class. What is shown here are 1000 samples uniformly drawn in the square, and the classification is also given. Okay. So, these are the sample set, and if I did an SVM with Gaussian kernel and after learning the SVM, if I flag only the support vectors, that is what I get. As you can see, the support vectors essentially define the class boundary. These are all the vectors that are closest to the class boundary. Of course, I have used a Gaussian kernel. So, I am working in a very high dimensional space, learning a hyperplane there, but then the patterns that are closest to that hyperplane are these patterns. So, essentially support vectors give me a very good idea of the geometry of the class boundary. Okay. of course pictorially. Here is another example, slightly more complicated. Actually, it looks like a mess here. I plotted 2500 sample points. This is actually a 4 by 4 checkerboard. There is a 4 by 4 grid where alternate squares are different classes. So, this is one class, that is another class, that is one class, that is another class, and so on. Right? This is one class, that is another class. Once again, this is class 1 and that is class 2, and so on. This is a 4 by 4 square. Once again, using Gaussian kernel, if I learn SVM and then plot the support vectors, those are the support vectors. As you can once again see, I have neatly pulled out only the vectors which are closest to the class bound. Rest of them can all be thrown out now. So, in this sense, not only SVMs do a good classification, in both these cases the SVM classification is has very high accuracy, but in addition the support vectors themselves are a very useful extra information that we get out of this method. Okay. The basic idea in support vector machines, as we seen, is the kernel function, that is what makes the method competitive. The idea of kernel functions can be extended in many ways, right. So, basically what do the extensions mean? Basically I can reformulate the SVM problem. So, some of them are, you can reformulate the SVM problem so that I get maybe only an approximate optimal hyperplane, but the algorithm is more efficient, or I reformulate exactly in the sense I still get the optimal hyperplane, but I can add some additional features to the original SVM method. There are many variations like this today. For this course, to stick to our time and other constraints, I am just going to illustrate it with just 2 simple examples, one of each kind. Okay. Here is, this is the way one does these things. So, I start with the basic SVM optimization problem, and then I change the optimization problem in some ways, which is useful to me. Okay. So, here is one way. My original optimization problem is half W transport W plus C times Ji, minimize that subject to the supportability constraint y and W transport Xi plus B greater than 1 minus Ji and Ji greater than or equal to 0. That is the standard SVM problem with penalty constant. I added a B square. The idea is I am having only my actual classifier is W transpose X plus B, but I am using only W transpose W. Why not I use B square? Now, I know why I put W transpose W, because that is the margin that I am minimizing. B square has nothing to do there, but let us say we put the B square term anyway, right, just like that we put the B square term. Then what happens? What happens is, this is what turns out to be the dual. Your objective function has not changed, I mean not has not changed, this term is same as earlier, this term is same as earlier, I am just adding one more term in the objective function, mu I, mu j, y I, y j. And this is also a quadratic term, it makes no difference adding one more term into this quadratic term. But what I gain is that the equality constraint is lost. There is no longer the equality constraint in the dual, only bound constraints. Why is such a great thing? Now, it is no different from just minimizing unconstrained way a quadratic function. For example, I can do gradient descent on this. If I do gradient descent on this, normally in a constrained gradient descent I do gradient projection. What do? From the current point I calculate the gradient direction, move along the thing, wherever I go, from there I have to project myself back onto the feasibility region. Now, if the feasibility region is crazy, I do not know how to project myself, but if the feasibility is only about bound constraints, then what it means is I start from some mu, travel along the gradient, then at that point if any of the mu's is less than 0, I make that 0, if any of the mu's is greater than C, I make it C. That is all that projecting back into this constrained region means. Matter of fact, I can do better than that, because it is a quadratic function. If I take its gradient and equate to 0, I get a set of linear equations. So, actually to solve a set of linear equations subject to these constraints. Now, I can easily solve a set of linear equations by many relaxation methods, right. Gauss-Seidel relaxation, for example. Gauss-Seidel relaxation simply says I start with some point, some solution point, then calculate the new value for the first variable from the first equation by using the old values of all the other things. Now, for this new value for the second variable from the second equation and so on, right. And if it's very easy for me to implement this constraint, because after every time I calculate the update for mu, I have to just clip it between 0 and c. If the update turns out to be negative, I make it 0. If it turns out to be greater than c, I make it c, right. So, I can just take the gradient, which becomes just a set of linear equations, and I can solve the linear equations under this bound constraint using a simple algorithm such as Gauss-Seidel relaxation, where iteratively I keep finding new values for variables by using one equation for one variable, right. It is called successive order relaxation. This makes very efficient algorithm. It is much more efficient, almost 10 times more efficient than SMO. Okay. But the problem is that it is not solving the problem I am interested in, right. I mean, of course, it is giving me a very efficient algorithm for solving a different problem. Okay. What is this B square doing? Will that still give me optimal hyperplane? Of course, it does not, because my optimal hyperplane is a solution of the optimization problem with the B square not there. But what can be shown is that if I do it with a B square, I will not be too far away from the optimal hyperplane. So, I get only approximate optimal hyperplane, a fairly good approximation, and the price I am paying, I mean the advantage I am gaining for being only approximately correct on the optimal hyperplane is that solving my dual optimization problem is very efficient. So, this is one way one can reformulate. We will look at another reformulation now, which is called the new SVM, and most people think that this new is a pun on the guys who proposed this new SVM. Okay. The idea behind the motivation behind new SVM is as follows. This is the primal objective problem that we need, that we seek to solve for SVM. Here I put phi xi instead of xi, because we are essentially learning this optimal hyperplane in a high dimensional space, and phi is the symbol for the transformation. Basically, this is the margin, and basically we put ji because we do not know whether things are separable or not. So, we use the slack variables ji. The problem with this optimization is I do not know how to choose c. C is a kind of an exchange rate between margin and some measure of error, and the measure of error is very crazy here, because ji greater than 0 does not mean that I am actually making an error. If ji is greater than 0 but less than 1, the corresponding xi y is correctly classified, but it still adds to error, and it does not tell me how many I am incorrectly classifying, right. Instead of misclassifying only one, but misclassifying by a large margin, I may settle for something that classifies 100, misclassifies 100 patterns, but each one by a small margin because of this. This summation ji, I really do not know what it is doing. So, I cannot give any physical meaning to C. All I know is if C is very large, I will not tolerate any errors. Except for that, I have very little idea whether I should choose C to be 5 or 10 and what are the trade-offs, right. So, one problem with the SVM formulation slack variables is we do not have good guidelines on how to choose C. It is very difficult to give guidelines because C does not have any simple interpretation. So, let us say we want to work with a optimization problem in which the user defined constant like C has some meaning. So, I reformulate the primal object function like this. I still have of W transport W, I still have summation ji. Instead of C, I put 1 by n here, where n is the number of examples, and I add one extra term minus nu rho. Nu is the parameter. Instead of C, my new parameter is nu is used. Rho is also an optimization variable. Now, in addition to W, B and ji, I have added one more optimization variable rho, and rho comes here in place of 1. So, instead of demanding y and double transpose phi xi plus b greater than 1 minus j, I am saying it should be greater than rho minus j. So, whether the margin is with respect to hyperplanes that are one distance away or rho distance away, I do not know. I am just saying take it rho distance away and optimize on rho also. Right. Now, okay, let us just consider this problem as it is, and of course, if I want rho to put the place of 1, and know that is what defines the margin. Then do I need rho greater than 0? I do not need rho greater than 0 for the following reason. This optimization problem is very cleverly chosen. Given this problem, if the point W is all components of W is equal to 0, B equal to 0, all components of J equal to 0 and rho equal to 0, those are my optimization variables, all 0 is a feasible point, right, because it satisfies all the constraints. Because all 0 is feasible point, and at that point the objective function has value 0, which means the actual minimum, okay, cannot be positive, because I already know one feasible point at which the objective function has value 0, right. No strictly positive value can be its minimum. Now, if I choose rho greater than 0, this term will be positive. I know W transport W is positive, I know J i's are positive. So, if I choose any rho greater than 0, this will be strictly greater than 0. Now, such a point can never be the solution of this optimization problem, because I know a feasible point at which the objective function has value 0. So, we do not need rho greater than 0 constraint at all, we can just minimize unconstrainedly on rho. Okay. So, let us start with this problem and form its Lagrangian. So, recall that I have W, B, J, rho 4 optimization variables, then I have n constraints like this, right, another n constraint like this. I have to write all my constraints in less than or equal to 0 form. So, this constraint becomes rho minus J I minus y into W transpose phi x I plus b less than or equal to 0. This constraint becomes minus J I less than or equal to 0. Also recall that we are putting phi x I here. So, that we are already using the kernel trick. I mean, we ultimately will put the kernel there, but we are keeping the notation so that we are conscious that the formulation is in a transform space. Okay. So, with all this, this will be my Lagrangian. This is objective function of W transpose W minus rho nu plus 1 by n summation J I minus eta I J I is for this constraint, minus J I less than or equal to 0, eta I are the corresponding Lagrange variables, and this is for this constraint summation mu I rho minus J I minus y I W transpose x I plus b. This is my Lagrangian, right. So, mu I are the Lagrange multipliers for the separability constraints and eta I the Lagrange multipliers for constraint J I greater than or equal to 0. Okay. Now, let us put the Kuhn-Tucker conditions for this. I have to first is, so derivative with respect to all the optimization variables should be 0 of L. So, gradient with respect to W is 0, del by del B is equal to 0, gradient with respect to J is equal to 0 and del L by del rho is equal to 0. Del by gradient with respect to W is equal to 0 gives us the old thing, because with respect to W nothing has changed. I get 1 W from here and I get summation mu I y I phi x I here. So, that will still give me this. Similarly, with respect to B also nothing has changed. So, I put B, I get that. With respect to J, so if I want to differentiate with respect to any particular J I get 1 by n from here, minus eta I from here and minus mu I from here. So, any derivative with respect to any J I will give me eta I plus mu I is equal to 1 by n. It is a very interesting thing. The two Lagrange multipliers of the two different constants, the primal, are linked like this. Okay. Similarly, del L by del rho will give me, if differentiate with respect to rho, will give me minus nu from here and summation mu I from here. So, this nu that I have chosen as a user different constant should be equal to summation I is equal to 1 to n mu I. That is a pretty interesting relationship. So, the Kuhn-Tucker condition specifies that summation mu I should be equal to nu. Then I have the feasibility, these are the two constraints that should be satisfied. Then the Lagrange multipliers for the inequality constraint should all be positive. Then I have the complementary slackness, because eta I is for the constraint J I greater than or equal to 0, eta I J I should be equal to 0. Similarly, mu I into this constraint should be equal to 0. These two are the complementary slackness conditions. Now, why is this interesting? Suppose J I greater than 0 for some I. So, if J I is greater than 0, then the corresponding eta I is equal to 0, because of the complementary slackness. Once the corresponding eta I is equal to 0, this tells me that the corresponding mu I should be equal to 1 by n. Right? And I also know that nu is equal to summation mu I. We can put all of this together. Suppose J I is greater than 0 for some I, then we have eta I equal to 0. and hence mu I is equal to 1 by n, and hence nu is equal to summation mu I. Now, the summation mu I can be written as summation over all those I such that j I greater than 0 and summation over all those I such that j I equal to 0, right. For some I j I will be 0, some I j I greater than or equal to 0. Now, mu i's are positive. So, I can, if I drop this term is all right, I am only finding a lower bound. So, I can always write this plus this is greater than or equal to summation only this term, and this term has a very interesting structure. When j I greater than 0, mu I is equal to 1 by n. So, each of these terms will be 1 by n. How many such terms are there? As many I as there are j I greater than 0. So, I can say this is the cardinality of the set of I such that j I greater than 0. This is the number of I for which j I greater than 0 by n. What does j I greater than 0 means? On that particular example x I y I, there is a margin error, that is I am actually do not have as much margin as I want, that is j i's are slack variables, j I will be greater than 0 only if I am making an error on the corresponding x I y I. So, this numerator here is nothing but the number of examples on which I made error, right. So, what we have is that nu is greater than or equal to the fraction of margin errors. So, the nu that I have chosen is such that it has to be greater than or equal to the number of margin errors. So, if I chose nu to be 0.1 when I am solving this problem, that means I will not allow, that means my optimization problem guarantees that any solution I get is such that the number of I for which I have made margin errors is less than 10%. Right? So, nu is an upper bound on the fraction of margin errors. That is not all. We also know that for all I, whether or not j I greater than 0, mu I is between 0 and 1 by n, and we know nu is equal to summation mu I. So, I can once again split that to mu I such that mu I greater than 0, mu I such that mu I equal to 0, this term does not matter really, and for all these mu I know it is less than or equal to 1 by n. So, I can write it less than or equal to mu I such that mu I greater than 0, and we know what are mu I greater than 0, they are support vectors, right. So, nu is also, so because each mu I is less than or equal to 1 by n, summation mu I is less than or equal to 1 by n times the number of things in the summation, and number of things in the summation is number of I such that mu I greater than 0, that is equal to the number of support vectors. So, nu is a lower bound on the fraction of support vectors, that is nu is always less than or equal to fraction of support vectors. So, if I choose nu to be 1, I am asking the optimization, I formulate the optimal problem such that at the optimum point the fraction of support vector should be at least 10% and the number of margin errors have to be at most 10%. Matter of fact, one can show that asymptotically as the number of examples goes to infinity, nu will be actually equal to both these fractions. Nu will be equal to the fraction of support vectors and fraction of margin errors. That is very useful. So, I can decide what kind of performance I want, right, by choosing my nu. So, the nu in SVM formulation, in the nu SVM formulation, the nu is a user chosen constant, and unlike the parameter c, the nu has interesting interpretation. Nu will be between 0 and 1, and if nu is not between 0 and 1, this will not have a solution, because nu has to be equal to summation mu I, and mu I are always between 0 and 1 by n. And given that nu between 0 and 1, it is simultaneously it's a lower bound on the fraction of support vectors and is an upper bound on the fraction of margin errors. Okay. Simultaneously an upper bound on the fraction of errors and lower bound on the fraction of support vectors. So, what it means is if for the chosen nu, the problem has a solution with rho greater than 0. Of course, if I choose an unattainable nu, I cannot get a solution, but what do you mean by I cannot get a solution? It always has a feasible point, so I will get a solution, but the solution will be trivial, I will get rho is equal to 0. Right. But if I get a solution with rho greater than 0, then the bounds would be met. Right. This gives us a very good way of choosing the penalty constant. Unlike C, I can choose nu, right, and because I have now a good idea of, so if I am willing to tolerate maybe at most 10% margin errors, then I choose nu to be 0.1. I solve it. suppose on this problem I cannot get a solution where I can only misclassify 10% points, it turns out that the row that I get would be 0. So, maybe I will change the 10% nu to 15% nu, right. But the nu has a nice interpretation, and hence in that sense is much easier to choose than the penalty constant C. This is the real utility of the nu SVM. Okay. So, can it be solved easily? See, my primal problem now looks much different from the old primal problem of old SVM, because I get a minus rho new row here and I change this to rho, but much more importantly, unlike the old SVM, it has one more optimization variable. But as it turns out, if I take the dual looks no different. This is the dual for us. All that happened was the quadratic term in the dual still stays mu I mu j y I y j k x I x j with a minus term. The linear term summation mu I goes away, okay, does not matter. Now, I still have the old inequality constraint I is equal to 1 to n mu I y is equal to 0, the old equality constraint. Then I still have bound constraint, but not there is no C now, that what was there before summation j I is 1 by n. So, I get mu I to be between 0 and 1 by n, and I get this extra constraint summation I is equal to 1 to n mu I is equal to nu. So, it is exactly same as the old SVM. This extra row that I have put in really makes no difference. The objective function is still quadratic, and I still have similar kind of linear equality constraints and bound constraints on the variables, right. So, it is a simple optimization problem similar to that of old SVM. So, it is very easy to solve. Once again, the dimensionality is only n and so on and so forth, right. One can also show that this is not any approximation like the previous one I considered. If suppose you have a solution for nu SVM, and ultimately once we solve, we will not only get mu s, but also get rho, and let us say the rho is strictly greater than 0, that is what we mean by a solution for nu SVM. Then I go back to the old SVM formulation, there I choose C is equal to 1 by rho times n is the number of examples. Then one can show that you get the same solution with that old SVM algorithm as you got for nu SVM. So, this nu SVM essentially gives you a solution that you could have got for a particular value of C. In that sense, unlike adding b square in the object function, I am not doing any approximation, but what I have done is I have really cleaned up the formulation of SVM, because unlike the penalty constant C, the user defined constant nu here has some interpretation. Okay. Now, this idea can be extended to regression problem also. Just like you have got nu SVM, I can have nu support vector regression algorithm, let us call it nu SVR. In the regression problem, what are the user defined constants? One is epsilon. Epsilon tells me, see, if you recall your support vector regression algorithm, we are using the so called epsilon insensitive loss function. So, in that sense, epsilon tells me the allowable error range. If the actual value, the difference between the actual value and my prediction is less than epsilon, I suffer no loss, unlike in the least squares case. So, to make a good guess on epsilon, on this problem, if I put epsilon very large, then useless predictions will come. On the other hand, if I put epsilon very small, I may not be able to find a nice function which predicts to that level of accuracy. So, because up to epsilon the loss function gives me 0 loss, I should use epsilon very intelligently. And once again, like the C there, here the C is not the real issue, the epsilon is the one that is telling me how I am trading accuracy, and I have no guidelines, right. Epsilon specifies the tolerance, tolerable error, and is once again difficult to know for this data set what is a tolerable error. So, like in the nu SVM case, we can reformulate support vector regression, so that just like we added rho instead of 1 there and made rho as a optimization variable, we can add epsilon as an optimization variable here. Okay. This will give me something very similar to SVM, nu SVM, it is like this. So, once again this is my old SVR optimization, half W transport W, which we added as a regularization parameter. We already seen this is like the epsilon margin of a function, C times this, because this is simply a way to implement the epsilon insensitive loss function. So, if modulus of yi minus W transpose phi xi minus b is less than epsilon, then both Ji and Ji prime are 0. If on one side it is not less than epsilon, then the corresponding Ji will come here. Okay. So, this is my whole formulation of the slack variables. Now, in the new formulation, I want to optimize on epsilon also. So, I add epsilon as an extra parameter for optimizing, and I put new epsilon inside here. Otherwise, the constraints remain the same, epsilon just became an optimization variables, and I am just saying on the C side, in addition to your old parameters, I put new epsilon, where new is a user chosen constant. The dual for this once again turns out to be quadratic. It got once again very simple structure, very similar to the old new SVR. I won't go into details because it's pointless, but the thing to recognize is that the objective function is still has one linear term and one quadratic term, and all constraints are linear. So, this is once again a very good nice optimization problem, and one can show that you get similar results as in new SVR, right. The whole idea of why we did this is same as in SVM case, where we want to have a handle on allowable accuracy, right. So, we want to choose new based on how much accuracy we are looking for in our predictions, right. So, that I correctly optimize my epsilon tolerance limit. So, this turns out to be true, this turns out to have similar kind of properties as the new SVM case. That is to say, in the new SVR, suppose new SVR leads to solution W bar, B bar, epsilon bar with epsilon bar strictly, just like in the new SVM, if I choose a wrong new, I will not get a solution, in the sense I get a solution with rho is equal to 0. Similarly, here. So, when I get a solution with epsilon strictly greater than 0, then if I now run the old SVR with that value of epsilon and the same values for the other constant C, then I get back the same solution, right. So, one like new SVR also gives you a solution that old SVR could have given under some particular parameter settings. The only thing is we beforehand do not know how to set this parameter, because for this data set we do not know what is the tolerable error. That is why new SVM is good, except that once I get a particular epsilon bar, for that epsilon bar I get the same solution in the whole new SVR also. So, this is a actual exact formulation. And once again you can show that nu is an upper bound on the fraction of errors, meaning number of points on which prediction is greater than epsilon, and lower bound on the fraction of support vectors, right. And like earlier, if you have sufficiently good data sets, sufficiently good meaning you have large number of IID examples and your class conditional density satisfies some proper conditions, then in such cases nu simultaneously equals both fractions asymptotically. So, as the number of examples goes to infinity, nu is actually equal to the fraction of support vectors as well as the fraction of errors. So, like in SVM, it becomes very easy to decide how to choose the required constants by the user, right. So, this is an example of just reformulating the optimization problem for SVM, so that the resulting optimization problem is a lot easier to choose the user defined constants, but at the same time we are still getting the same solution as the old SVM. Okay, same solution meaning same solution at some parameter setting. So, we are not really sacrificing the idea of getting optimal hyperplane, but this allows us to choose our parameters much more simply. So, nu is much more easier to choose than the penalty constant C. Okay. Now, we will look at one more issue with SVMs. We posed SVM support vector regression problem as a risk minimization under a special loss function, namely the epsilon insensitive loss function, and then reformulate it as an equivalent constraint optimization problem. For the support vector machine, namely the classification problem, we directly pose the optimal hyperplane problem as a constraint optimization problem. Among all hyperplanes that satisfy the separability constraint, find the one with minimum margin, right. But now we know the connection between constraint optimization, equivalent and constraint optimization problems, at least sometimes they can exist. So, one can ask, is SVM, can SVM be written like a risk minimizer? As it turns out, yes, SVM is also an empirical risk minimization algorithm under a special loss function. Okay. So, let us look at the SVM again. This is the SVM primal optimization problem of W transport W plus Ci with these constraints. So, what do the constraints mean? The constraints mean, if you give me a particular W on B, the Ji's that I have to choose to maintain feasibility are such that Ji has to be greater than 0 and Ji has to be greater than 1 minus y into W transport Xi plus B. So, Ji has to be greater than maximum of 0 comma 1 minus y and W transport Xi plus B. Ultimately, I am minimizing summation Ji. So, as long Ji can be anything greater than this. So, the best Ji is to just simply choose this, because Ji has to be greater than or equal to this, and I am minimizing summation Ji. I just need to choose this as my Ji. So, given a WB, this is the best choice for Ji, and once I know that the best choice for Ji, I can put it there. Once I put it there, I have used up the constraints now. So, I can just do a unconstrained optimization. So, what this means is that solving the SVM problem, this constraint optimization is same as solving this unconstrained optimization. Instead of summation Ji, each Ji has to take only this value, max of this. So, now I do not need these constraints anymore. Once it takes this with respect to the W on B and the corresponding Ji, it satisfies these constraints. So, my SVM problem is same as solving the unconstrained optimization problem of minimize over WB of W transport W plus C I is equal to 1 to n max of this, max of 0 comma 1 minus phi and W transport Xi plus B. Now, the model we used is Fx of W transpose X plus B. So, this term is like something between yi and Fxi. This is Fxi. So, 1 minus yi Fxi, this is some function of yi and Fxi. So, this can be a loss function. If this is a loss function, this should be the regularization term, right. Of course, where that C comes is a matter of convenience. So, this, and we know that is a regularization term, because for this model, we already know that W transpose W is a good regularization term, right. So, this must be the empirical risk. So, is this empirical risk? Yes, of course, it is empirical risk with respect to a particular loss function that we have seen earlier when we studied loss functions, is called the hinge loss. So, hinge loss for xy for a model f is L of y comma fx is max of 0 comma 1 minus y into fx. That is what we have here. That is what exactly max of 0 comma 1 minus y into fx, yi fxi. Right. So, that is the hinge loss. So, with respect to hinge loss, if I want to do regularized risk minimization, what should I do? Minimize over WB 1 by n, because the empirical risk I is equal to 1 to n, L of yi fxi plus some constant times half W transport W, because that is the regularization term. L of yi comma fxi is nothing but max 0 comma 1 minus yi fxi. That is what I have here, right. So, which means our SVM formulation is nothing but empirical risk minimization under the hinge loss along with the regularization. So, SVM is also no different from empirical risk minimization. It is just doing empirical risk minimization under a special loss function called hinge loss, which we already seen as an example loss function when we consider loss function. Matter of fact, I told you that this is a convex loss unlike the 0,1 loss function, right. As we saw, the hinge loss and square loss are good convex approximations of the 0,1 loss. When we study loss functions, we said the 0,1 loss is nice, because minimizing 0,1 loss gives you classified with minimum probability classification, but 0,1 loss is non-convex and hence is good to have some convex loss functions, right. So, let us just recall this 0,1 loss function is one, we are considering y is plus 1 minus 1, right. So, and our classifier is sin of fx, that is our model. So, 0,1 loss function is if y and fx are the same sign, then there is no loss, otherwise there is a loss. So, is 1 if y fx is negative and 0 otherwise. As we already seen, square error loss can be written like this, because when y is 1, it is 1 minus fx whole square, when y is minus 1, is minus 1 minus fx whole square is the same as 1 plus fx whole square. So, this is the square loss function. This as we have seen the hinge loss. We can plot all this, right. So, that is the 0 1 loss function plotted on the x axis I am plotting y into fx, on the y axis I am plotting the loss function y comma fx. So, that is the 0 1 loss function, but that is non convex. So, squared error is one way of convexifying it, and the hinge loss is another way of convexifying it. Square loss is what neural networks minimize, hinge loss is what SVM is minimizing, right. Because I convexified it nice in SVM, because that is both pieces are linear, I get a very nice optimization solution. As we saw, the empirical risk under regularize the empirical risk under hinge loss can be rewritten equivalently as a constraint optimization problem, which can be solved very efficiently. Okay. Hinge loss is also called soft margin loss. Suppose we are actually minimizing expectation with respect to soft margin loss, say y is plus 1. So, we want to find a model such that we want to minimize expectation of max 0 comma 1 minus y f x. What is our best bet? We want always this max 0 comma something to be 0. So, we want this to be always positive if possible. That I can do if I always make y and f x are the same sign. Right. So, essentially what it means is that the best f is such that if probability y is equal to plus 1 is greater than 0.5 given a particular x, for that x f x should be greater than 0 and vice versa. So, this is a very nice classifier, right. This is essentially base optimal classifier. If the positive probability is greater than 0.5, I go for that class, right. So, essentially minimizing expectation under hinge loss also gives us, just like under 0 1 loss, gives us a fairly good classifier. Okay. That is one other way of looking at why SVMs perform better. Okay. So, to go further on this, let us see that SVM method has two important ingredients. One is the kernel function. The kernel function allows us to learn nonlinear models using essentially linear techniques. The second one is the support vector expansion. The final model is expressed as a linear combination of data vectors and often sparse, because many of the Lagrange multipliers may be 0 except for the support vectors, for the rest of them Lagrange multipliers are 0. So, there is the support vector expansion. The final model is expressed as a sparse linear combination of the examples. Both these are very useful things, right. Now, in general also these are good. Kernels are good way to capture similarity and are useful in general. Support vector expansion is also a general property of kernel based methods. So, in the next lecture, we will look at these two in detail. We will look at capturing general similarities using kernels and also when all such support vector expansions occur. So, next lecture we will use slightly more theoretical tools and look at kernel based methods in general. Thank you.